Simulation and emulation are very important tools in SoC design. They are used extensively throughout the design cycle before and after tape-out. Hello and welcome to our talk, Functional Debug, Verification and Beyond. My name is Hanan Moller. I'm a systems architect and a technical director for the Embedded Analytics Application Engineering Group at Tessent Silicon Lifecycle Solutions, Siemens. Today we will talk about the complexity of modern SoCs and some of the challenges of multi-core SoC designs. We will explore some of the limitations of simulation and emulation in addressing those challenges. After discussing some of the traditional debug and bring-up techniques, we will introduce embedded analytics, a new approach and a set of tools to implement functional debug as a way of reducing the impact of the complexity. Embedded analytics is part of Siemens EDA's Silicon Lifecycle Solutions. Some of the major industry trends include applications in areas such as AI and machine learning, 5G infrastructure and edge devices, and connected autonomous vehicles. Those applications make use of new architectures such as tensor processing units, neural network processors, and others. Smaller design geometries in those new architectures result in devices with transistor counts in the tens of billions. Further increasing the complexity of systems are new ways for connecting and packaging devices, 2D and 3D stacking, chiplets, and more. Looking at two specific examples of SoCs, Esperanto Technologies ET SoC1 contains more than 1,000 custom RISC-V cores. The main application for this device is accelerating machine learning applications. Fabricated at 7 nanometers, this device contains almost 24 billion transistors. Another example is the wafer scale engine from Cerebras Systems, a system designed for accelerating deep learning. These types of designs are introducing new scaling challenges on multiple fronts. On the technology front, we need to address new kinds of defects and fault models with higher physical failure analysis costs. Our design and verification methodologies need to scale up for better modularity with increasingly higher number of gates per device bin. We need to accept that we may not be able to fully verify some parts of the design and that we will have increasingly lower external visibility. At a system level, new use cases will pop up during the device and system lifetimes. All those use cases need to meet increasing resilience requirements with important uptime, safety, and security goals. Addressing these challenges is an important part of Siemens EDA's Silicon Lifecycle Solutions approach. Let's now look at some of the challenges in the design of multi-core SoCs. Life for chip designers is not getting easier. Designer must juggle many different inputs against diverse output requirements. When a company is putting together a new system on a chip, they'll be sourcing their IP from various different parties, both internal and external. There are often hundreds of IP blocks within a given SoC. The same goes for their system software, which is often assembled from many resources, increasingly with open source content. Different operating systems with different memory requirements and different time constraints. An array of IP providers lead to chip architectures which are heterogeneous. They are often based on 2 or more process architectures with multiple CPU instances. SoC designers have to validate their design at chip and system level while all the time optimizing for best performance and dealing with the additional complexity of how the hardware interacts with software throughout software development, optimization, and deployment. In the same way that building an SoC is more than just about the CPU cores, so are analytics and debug. Understanding the behavior of complex systems is a challenge. There are many hardware blocks interacting with each other, often under software control. The systems often do not behave as expected. All those interactions between different core software, peripherals, real-time events, poor implementation, or some combination of all of the above, all contributing to bad behavior. Providing visibility of SoC behavior is important. It needs to be done in an intelligent manner and without swamping the system with vast amounts of data. The core is but a small part of the overall SoC. Analytics and debug are more than just run control. It is more than just CPU-centric information such as instruction trace, which is important. Run control and trace are important and of course have their place, but are only part of the overall analytics solution. Gaining meaningful insight into the interaction within the SoC requires a holistic approach. We need to have a unified and uniform programming model for all the analytics IP. The analytics IP need to be agnostic to underlying hardware and to the IP providers. It is really important that the planning and execution of the analytics IP is there throughout the design cycle and not coming at the end as an afterthought. Simulation and emulation are very important tools in the SoC design. They are used extensively throughout the design cycle before and after tape-out. Simulation gives excellent visibility into the design, but is slow. Emulation is order of magnitude faster, but is still not running at full SoC speed. Neither simulation nor emulation is going away anytime soon. Both play a critical role in IP and SOC verification. However, as both are only a proxy for what happens in an actual system, they are not sufficient for many analytics use cases, especially those which are taking place after the SoC has been deployed. To really test your application on silicon, you need to have the silicon. To really characterize your application on your silicon, you need to embed analysis capabilities into your silicon. So what is functional debug? Functional debug helps ascertain that the SoC is working to the specification. It aids in capturing rich data at speed from within the SoC, collects performance data in a non-intrusive manner, feeds information to the system architects, design teams, and firmware and software teams, helping derive insights into system behavior, benefiting the design throughout the product lifecycle. The embedded analytics solution enables functional debug. It provides IP to capture and communicate the information and software tools to help analyze the data. In this part of the talk, we will describe the embedded analytics IP and its key characteristics. We will see how it can be used alongside simulation and emulation and explore some practical use cases where embedded analytics IP can help in SoC performance optimization. Here we have a generic SoC. It contains some CPU clusters, safety and security subsystems, memory, vision subsystem, accelerate subsystem, a NOC, some high-speed IOs, and a peripheral subsystem. To be able to address some of the complexity we had discussed earlier, we will want to provide visibility into activity in different parts of the SoC. This includes monitoring bus activity in different locations in the system, for example, at the boundary of the NOC, or maybe as being initiated from the accelerator subsystem. We will want to be observing status signals and state transitions in different places in the system, and to collect processor trace in the use cases where that is required. One possible approach to addressing this visibility is to instantiate various embedded analytics IP instances in the system to collect the required information. Some of the technical problems that can be addressed using the embedded analytics IP include: why do some DMA transfers take too long? Can I trust system security? What is going on with my memory controller? Why does the system occasionally hang or deadlock? Is that bus transaction authorized? Why is the CPU not as fast as expected? Let's do a quick run through of the embedded analytics hardware architecture and some of the IP that we provide. All the IP we provide is delivered as synthesizable Verilog RTL. This makes it technology independent and easy to integrate into your design. The green blocks here represent the main parts of your system. You may have several processors, accelerators, and many other types of IP. Some of the IP will have been purchased from third-party providers. Some of it will have been developed in-house. There are 4 families of IP in the test and embedded analytical portfolio. The first part includes our analytic modules. Some of the analytic modules are completely non-intrusive, whereby, for example, if we look at the bus monitor, they strictly observe an interface, and the bus monitor in particular is protocol aware, transaction aware, and is able to track transactions, trace them, measure, count, based on transaction criteria that you define when the system is running based on the use case of interest. Similarly, the status monitor over here can be used as an on-chip logic analyzer to observe signals on other blocks in your design. Other members of the analytic module family are related to interaction with processors. So, for example, the PAM is an IP which provides a gateway into a debug module of a processor, and we also have trace collection IP, whether it's a trace encoder for RISC-V type processors or a trace receiver for other industry standard trace protocols. Next, we have a flexible and scalable message fabric. The message fabric connects all of our IPs together and is used for the purposes of configuration, data collection, and cross-triggering. The cross-triggering feature is quite interesting in that it allows us to build very flexible monitoring scenarios where, for example, you may be monitoring using this bus monitor in here to look for a particular memory access by a particular CPU, and when that is being observed, generate a cross trigger to, let's say, enable or disable a particular trace from a particular core in your design. The next part of our portfolio includes a family of communicators. The communicators are the gateway between a software entity controlling the embedded analytics IP and collecting the information from it and the hardware itself. We support different kinds of communicators for different use cases. So, for example, for off-chip debug and analytics, we offer something like a JTAG communicator and a USB communicator. We also support use cases whereby the embedded analytics system is controlled by an on-chip resource, and that can be managed via the AXI bus communicator. We also support high-speed communicators such as an Aurora communicator and an EBC communicator, which is operating in conjunction with the USB 3 controllers. The last family that we want to talk about today are our active managers, where we have a bus sentry IP, which is used for a security solution whereby it can monitor accesses to a protected region of memory or protected peripheral and actively block transactions from going across. And also our lockstep manager, which is a solution for running and controlling 2 or more resources that need to operate in lockstep. We It is also worth mentioning that we include a system of message logs throughout the system. Those message logs allow you to lock down the entire embedded analytics infrastructure or just parts of it and protect the data that you are collecting or or not allow certain users in certain use cases from accessing the um, infrastructure. So here we see some of the key characteristics of the embedded analytics IP. The embedded analytics IP is real-time and non-intrusive. It does not impact your system performance or affect the signals being monitored. It provides for full visibility of your hardware and software, including their interactions. It allows for advanced analytics and forensics, as it does quite a lot of processing on chip. Therefore, less data, more useful data can be transferred off chip for analysis. It is ISA agnostic. The IP is not tied to a particular processor architecture and can deal and interact with different processor architecture and vendors. We provide high-speed debug over USB 2 and USB 3. The hardware is able to detect events at wire speed without having to stop the operation of the system to report them. We reduce trace bandwidth by having smart IP where it can filter, count, and perform the cross-triggering all in hardware without requiring expensive processor cycles to perform that. And the communication between the embedded analytics IP, as we've seen earlier, running over the message fabric, is done independent of the main interconnect and allows for complete separation of the actual functional traffic in the system and the debug and analytics traffic. Taking a new approach of functional debug through embedded analytics provides a holistic approach to performing that over an entire SoC in a way which is processor agnostic, non-intrusive, allows you to expose hardware and software interactions, and help reveal performance bottlenecks in your system. As we have described earlier, dealing with an SoC risk and complexity consume time, talent, and money. Using embedded analytics provides confidence of full visibility into every corner of the SoC, the power to unify data from different IP vendors, the insight into complex system interactions, the intelligence to know which data is important, the capability to act on critical insights, and the flexibility to integrate and build on a technology platform. It is important to remember that embedded analytics augments what we do during simulation and emulation by providing visibility into the SoC in silicon at runtime. In the next few slides, we will see how embedded analytics can be used during simulation and emulation and how tests can be developed in those environments and be portable to lab bring-up optimization and in-life use cases. For simulation with embedded analytics, well, as we know, simulation allows testing in advance of any hardware being available. It gives excellent visibility, but is quite slow. Various BFMs allow evaluation before the target system is ready. Simulation of an embedded analytics in conjunction with the customer design is the next step whereby some of the BFMs from the customer's design are replaced with the actual design and are using the actual customer code. Integrating and using embedded analytics into an emulation environment is as simple as using it in a simulation environment. All embedded analytics IP is emulator ready, written in standard Verilog. Tesson provides Synthesizable BFMs suitable for driving the communicators, whether this is JTAG, USB, or AXI communicators and others. Those BFMs for emulation are identical to those used in verification, so transition from one to the other is straightforward. Tests being developed for running on an emulator host can be the same as those developed for running in simulation and vice versa. We write many of our tests in Python using our PyLink software environment to communicate with the BFMs, and similar to how it's done in simulation environment, the communication between the test and the emulator is done over a DPI connection. It is interesting and important to note also that same tests can be reused with the SOC in lab and in life, so your investment in writing the test is maintained across multiple environments and use cases. As we can see in the diagram in here, one or more BFMs are instantiated along the SoC top level. The BFMs communicate with external software over a DPI connection. The software can interact with the remote machine over a TCP/IP network, and the debug software can be implemented using a lightweight Python PyLink environment, using our UD agent with Python scripting, or with our Ultra-developed 2 IDE product. Let us now take a look at some practical use cases requiring performance optimization in an SoC. Here we have an example of a typical modern SoC. It includes a vector processing subsystem and hardware accelerators, something one may find in machine learning SoCs, 5G SoCs, to name just a few application segments. There's an OS subsystem and a bare metal subsystem. Those two subsystems are orchestrating the work tasks of the vector processing subsystem and the accelerators. There are some high-speed interfaces for off-chip communication, PCI Express, Ethernet, and USB 3. The SoC uses multiple DDR controllers to support multiple memory channels, as well as a collection of other peripherals. System security is increasingly important and is addressed using entities such as the security engine, sometimes referred to as root of trust, or TEE, trusted execution environment, as well as more traditional fuse and OTP blocks. Let's look at some issues that SoC designers are experiencing. We will go through some examples shortly, and those will help identify some of these problems and point to some solutions. Consider caches, for example. Whilst caches can contribute to CPU performance in many cases, they can introduce undeterministic behavior. These can cause problems, especially in a real-time embedded system. Scheduling of tasks and workloads within a multi-core environment can be very challenging. We are not talking about operating system level scheduling, but rather scheduling of tasks between different cores and multiple accelerators, having to coordinate access to various shared resources. Deadlocks or system hangs are common examples that SoC designers have experienced. Where do the MIPS go, or why is the CPU not performing as expected? Understanding the root cause for this is key to getting your product out in time. The behavior of the NOC. Is the NOC oversubscribed, or maybe it is unbalanced? All these things feed into the final product, both in timeliness, but also how well it will perform. Let us now look at some example usage scenarios of embedded analytics technology that can help identify and solve some of these problems. In this example, we're going to look for system hang or deadlock. We do this by configuring the NOC bus monitor to look at transactions going by from the vector engine to the NOC. We configure the NOC monitor to take a copy of the transactions, put them in a circular buffer inside the monitor, and look for transactions whose response takes more than a certain amount of time. That time in itself is configurable at runtime. When the NOC monitor detects this condition, that is, the response takes more than this configured amount of time, then those transactions that led up to the hang or that deadlock are already in a circular buffer within the NOC bus monitor itself. Now those transactions can either be pushed out or pulled out via some software entity, either off-chip or on-chip, for further analysis. In this example, we're looking at the activity of one of the bare metal CPUs. Here we're taking an AXI bus monitor and looking at the iCache port, counting the number of transactions seen by that bus monitor in a window of time. When that window of time expires, the count that the bus monitor itself generates is sent across the message passing fabric I mentioned earlier, then out through the EBC, which then goes out through the USB controller. In this case, it is USB 3. By taking those counts, we can build a pie chart such as the one you see here on the top left. And this pie chart shows us that 8% of the time the branch predictor is mispredicting, while 12% of the time we're just suffering from misplacement of code. With armed with this information, we can go to our compiler writers and software engineers to write better hints to the branch predictor to potentially and hopefully eliminate this 8%. We can also get the bus monitor to do min-max average of the cache miss duration. Whilst the average might be fine, it is the maximum latency that you experience which will have a knock-on effect on the amount of work that the CPU will do. We can also get the data that this bus monitor generates and produce a histogram which shows the profile of all transactions seen over time. In this example, we're observing traffic coming out of the 2 vector processors and one of the scalar processors in the OS subsystem. Remember, the scalar processor over here is the one that's doing the orchestration of work between various system components. By configuring the NOC bus monitors to observe Snoop traffic as well as data cache traffic to and from these processors, we can plot charts such as the one seen here on the left-hand side with the data collected by those monitors. What these graphs can tell us in here is that some of the behavior around CPU number 1 is a bit anomalous. It is getting a lot of snoops from CPU 0. All this extra NOC traffic increases the cache latency and reduces the performance for CPU number 1. What that means is that it would be useful for the software system architect to review how code partitioning is happening in the system and improve it to increase and enhance the throughput of the system. In this example, we are configuring the NOC bus monitors to look at link credits and link activity. Within the NOC itself, we have those much simpler NOC monitors that are observing the credits inside the NOC. We're looking at various different kinds of credits inside the NOC, in this particular example, per channel credits. By looking at this collected data, we can see that at this NOC monitor point over here, we have a poor supply of Snoop credits and write data channel credits. This could suggest that the CPU at that particular point is the target of more Snoops than it can handle. However, looking at the bottom graph at link activity, we can see that the write data channel is heavily loaded within the system, which may explain the behavior relating to the poor supply of write data credits. In this example, we are observing the execution of one of the vector engines. We have configured the processor trace encoder to be in cycle accurate mode, observing the execution of a particular function or when the CPU executes from a particular memory location. The packets of information that this trace encoder generates will be transported onto the message passing fabric, which then will forward them to the EBC, which then means that the USB 3 controller will send them out via the USB 3 PHY. At the same time, we have a status monitor looking at activity within the accelerators. What we have in here, in this particular case, is the status monitor looking at when a particular accelerator starts working and when it finishes its work. From that data that the status monitor generates, in effect, it gives us a start-finish time for each of the accelerator activity units or workloads. We can plot a chart like the one shown here at the bottom. We can see that most of the time, all the accelerators seem to be doing roughly about the same amount of work, except the case for accelerator number 1 here, where the penultimate workload takes a much longer time. And the consequence of that is that the execution of the instruction in the vector engine has stalled waiting for work to finish in the accelerator. We can see that in the decoded information that the debugger is displaying in the upper text window, where this particular instruction took a really long number of clock cycles. So hopefully the examples we have just looked at give you a good idea of the capabilities of embedded analytics architecture. In summary, one of the main challenges in SoC design and deployment is systemic complexity. This complexity arises from processor-to-processor interactions, hardware-software interactions, the performance and capabilities of the NOC, and so on. New use cases, post-silicon and in-field, need to be implemented and optimized. This can place limits on the design and system scaling. Addressing the complexity in a timely fashion translates to quicker deployment and thus into revenue. Embedded Analytics provides a full-speed, coherent, system-wide, and non-intrusive monitoring system. It enables on-chip, in-application collection of data and allows for analysis and use of data sciences and ML techniques to help identify problems as early and efficiently as possible. Thank you very much for listening. If you have any questions, please reach out to the email address on the screen. Thank you.